Hello everyone, welcome back to MP Coding, the Linux driver development with Raspberry Pi tutorial series. So far, we have covered Section 0, Introduction and Preparation, and Section 1, Raspberry Pi Setup. Then, in Section 2, we discussed the Character Device Driver Foundation. Today, we start Section 3, Real Hardware, GPIO, Interrupts, and Timers. In today's video, let's look at a GPIO control example. Here we will look at GPIO request and release, also set and get, of the GPIO state. First of all, let me show you that GPIO chips are available on my Raspberry Pi board. Open a terminal, type GPIO detect, and press enter. As you can see, my Raspberry Pi 4 has two GPIO chips, GPIO chip 0 and GPIO chip 1. Chip 0, labeled as Pin Control BCM2711, is the main GPIO controller for the BCM2711 system on chip. Chip 1, labeled as Raspberry Pi EXP GPIO, is a virtual or expander GPIO chip managed by the Raspberry Pi firmware. Chip 0 has 58 lines. This means user-accessible pins, that is, the 28 pins available on the physical 40-pin header, BCM GPIO 0 through 27, belong to this chip. The remaining GPIO lines, from 28 to 57, are used internally by the system for things like Bluetooth, Wi-Fi, and SD card communication. Chip 1. 8 GPIO lines are not connected to the physical 40-pin header. Instead, they are used internally for board-specific functions. On a standard Raspberry Pi 4, these lines commonly control things like the power LED, detect the USB-C power status, or manage power for the camera and display interfaces. If we navigate to the System GPIO class, cd/sys/class/GPIO, and list the contents of this directory, we can see entries like GPIO chip 512 and GPIO chip 570. The numbers may be different on your system, and that's perfectly normal. This number, 512, is the base offset for GPIO chip 0. So if we want to access GPIO 0 of this chip, we use GPIO number 512. Similarly, GPIO 1 would be GPIO number 513, and so on. The same concept applies to GPIO chip 1 as well, which starts at a different base number, 570. If we read the label of the GPIO chip 512 node, we can see that it is actually pin control, BCM2711, which corresponds to GPIO chip 0. Similarly, GPIO chip 570 is labeled as Raspberry Pi EXP GPIO, which corresponds to GPIO chip 1. Let's start to code. First, let me show you how I connected the GPIO pins in this example. I have connected GPIO 21 to an LED to configure as a GPIO output, and GPIO 22 a push button to configure as a GPIO input. I have created a new folder called GPIO, and inside it, a subfolder named request_free. Inside this folder, I created the make file and the source file. Right now, this source file contains only empty init and exit functions. In this example, I will show you how to request a GPIO and how to free that GPIO when the module is removed. Okay, let's start. First, I will define LED_GPIO as 21 and button_GPIO as 20. Next, I will define the base offset for GPIO chip 0. In my case, this offset value is 512. Define GPIO_offset 512. Then, I will create two static integer variables. The first one is LED_GPIO, which is the LED GPIO number plus the GPIO offset. The second one is button_GPIO, which is the button GPIO number plus the GPIO offset. To use the GPIO-related functions provided by the kernel, we need to include the linux/gpio.h header file. Now, inside the init function, I will first declare an integer variable called status to store the return values from the GPIO functions. I start by requesting the LED GPIO. GPIO_request. We need to pass the GPIO number and a string label for the pin. Here, I pass LED_GPIO and the label LED_GPIO. If the return value is not 0, it means an error occurred while requesting the GPIO. In that case, I print an error message and return a negative status value. Next, I set the direction of the LED GPIO. Since this is an output pin, I use GPIO_direction_output and pass the GPIO number and the initial state. Here, I set the initial value to 0, which turns the LED off. Now, I will repeat the same steps for the button GPIO. I copy the LED request code and paste it one more time. Change the GPIO number and label from LED to button. Since the button is an input, I set its direction using GPIO_direction_input. There is no need to pass an initial value for an input GPIO. Here, if an error occurs while requesting the button GPIO, we need to free the previously requested LED GPIO. For that, we use the GPIO_free function and pass the GPIO number that was already successfully requested. Now, I will set the LED output value to 1 using GPIO_set_value and pass the GPIO number along with the value. This will turn the LED on. Next, I will read and print the button state. For that, we use the GPIO_get_value function and pass the GPIO number. Finally, I will print a simple message to indicate that the init function has completed successfully. Now, in the exit function, I will first turn off the LED by setting its value to 0. Next, I will free both GPIO pins, the LED GPIO and the button GPIO, using the GPIO_free function. Finally, I print a message to indicate that the module has been unloaded successfully. Now, let's build the module and then load it into the kernel. I will open dmessage buffer in one terminal. Type make and hit enter to build the module. OK, build was successful. Now, load the module. Sudo insmod rek_free.ko and hit enter. You can see that the LED has turned on. And the button state is 0. So, the GPIO request is working correctly. Now, let's unload the module. You can see that the LED has turned off and the GPIOs have been freed correctly. Next, I will load the module again, this time while pressing the button. Now you can see that the button state is 1, which means the GPIO input is also working correctly. Next, I will show another method that does not require explicitly requesting GPIO pins. I have updated the code, so let's take a look at it. First, I removed the linux/gpio.h header and instead included the linux/gpio/consumer.h header. Here, I have added 2 pointers of type struct GPIO_desk, one for the LED and one for the button. These pointers will hold the kernel's internal GPIO descriptors for those pins. Now, inside the init function, I use the GPIO_to_desk function to get the GPIO_desk pointer for the LED GPIO. Here, did the same thing for the button GPIO. After this point, the rest of the logic is similar to what we did before. I set the GPIO directions, turn on the LED, and then read the button state. In the exit function, we don't need to free the GPIOs explicitly. That's because we didn't request them in the first place. So here, I simply turn off the LED and print a message. Let's make this new module. Load the module. As you can see, it works fine using this new method as well. Button input also works fine. So, what is the difference between the GPIO request method and the GPIO descriptor method? The GPIO_request method is the older, legacy GPIO interface. You work directly with GPIO numbers, and you must manually request and free each GPIO. The GPIO descriptor method, using GPIO_desk and GPIOD functions, is the newer and recommended approach. Instead of GPIO numbers, the kernel works with GPIO descriptors, which are safer and easier to manage. The request method is simple and good for quick tests or learning. The descriptor method is better for real drivers, especially when using the device tree or supporting different hardware. Today, we looked at GPIO control using a Linux device driver. In the next video, we will look at GPIO interrupt handling. So, thanks for watching. If you found this useful, like the video and subscribe to the channel. See you in the next video.